record this presentation in case so you can see it after in our channel, YouTube channel. And that's it. Juan, the ground is yours.
Okay, thank you. Thank you very much. Thank you everyone for assisting here. So I'm going to do a brief presentation about numerical modeling and how we can do a probabilistic assessment of the seismic hazard in underground excavations. So this presentation is basically about how we can mitigate those things we are looking there, those pictures, like 2 cases of rock burst. I'm sure you have seen or experienced some rock bursts on some way, and you know that we engineers we have to find ways to mitigate these things to happen. So usually, from a perspective of support, what is usually done is based on a magnitude. Uh, we consider a distance from the source of this. Sorry, give me one moment, please. Give me 1 second. There. So, there. So you consider the source, you consider the distance. So with the distance, you can calculate the attenuation of the vibration that the seismic event causes on the rock. And then you calculate how that energy that travels through the rock mass arrive at the edge of an excavation. And then all the rock that is damaged around the excavation, it's like excited by this energy traveling through the rock mass, and this tonnage here, these chunks of material, converts to an energy demand that is usually expressed in energy kilojoules by square meter. However, most of all of these parameters are not fixed values. They have a distribution of values. For example, magnitude. The maximum magnitude, as we will discuss later, is not one specific value. There is a distribution of values. Okay, some of those values are very likely, others are more difficult to occur, less probability, but there is a distribution of values. Same occurs with the distance from the seismic event to your excavation, and you have some variability, not because your excavation is going to move, but because your location of your seismic event has some error. And also, the seismic event is not just a point as it is usually seen on software. It's like a rupture that has a length, and also there is like the location error that the system located that here, but could be in another place. And also, because of rock mass heterogeneity and variability on properties and fracturing and all of that, also the damage around the excavation has a variability. Okay, so that means that at the end, your energy demand is not going to be just one value, it's going to be a distribution of values. So in this chart, we can see the probability of exceeding a specific energy. And some studies have shown that if you do the calculation from a deterministic point of view with average values, what you get is something like this. And in both cases, there's more or less like a 40%, 45% of probability of having an energy demand larger than the one that you calculate using the deterministic method. Okay, so there is an important probability of experience an energy demand larger than the one that you're using. So in this presentation, we're going to talk a bit about this part of the problem. How can you estimate the distribution of magnitudes, and how can you estimate that from numerical modeling, and how can you use that for further analysis? So the contents of this presentation, I'm going to make a very quick literature review about seismic hazard. So I'm not going to talk all about seismic hazard, but I will be very specific in some part that is important for this presentation. And also I'm going to talk how numerical modeling has addressed this seismic hazard problem. We'll talk about stochastic methods stochastic methods that work with numerical models, and we will check some of the methods that are more used, and we will and I will show you a new method that I found out where you can calculate the distribution of maximum magnitudes, but without having to explicitly create a complex numerical model. Okay, it's like an implicit solution. Then I will check out a couple of case studies, and finally a couple of conclusions about this work. So to start, I'm going to talk about seismic hazard. And as I mentioned, I'm not going to cover all the aspects of that, but I will talk briefly about something that is called the frequency magnitude distribution and the p-value. So in this picture, we can see here is like a side view of seismic events on a stope mine. So black points are seismic data, and the red circles are seismic events that are a bit larger. But using that seismic data, you can create an histogram of the frequency of the different magnitudes, how many events per magnitude range you have. But you can use that same data, that same histogram, you can create a cumulative chart. You can add this to this, and then this other, and adding from the largest to the smallest, and you can create something like that, a reverse cumulative chart. However, when we talk about seismicity, well, this chart means that there is like that number of events are above that magnitude, that number of events is above that magnitude, but we are the magnitudes we are looking for, that are the important magnitude for us, are those that are there. And in this chart, we lost the resolution of that part. So what we do to do like a zoom to the right part is to put the vertical axis in a logarithm scale, and we get something like that, and we can see a linear trend there, and that the data is the frequency magnitude distribution, and you can fit the straight line that's called the Gutenberg-Richter relationship. Okay, and that is characterized by the p-value, that is the slope of this line, and is usually in many sites the intersection point of this value of this line with this axis. This is usually understood as some people understand that intersection like the maximum magnitude that you could expect. However, we will see that that is not completely right, because we'll see that we can have a distribution of maximum magnitude. It's not just one single value. This frequency magnitude distribution of seismic events is based on how fractures distribute on your rock mass. The topic on how the fractures are distributed on the rock mass has been researched for a long time. There has been different models that describe how fractures distribute, from power law models, exponential models. However, Bonnet and others on 2001, they found out that the model that best represent the fracturing of rock mass, the size of the fracture, is a power law distribution. That is the one that you can see see there. So you can generate these fractures, and if you can put these fractures into a numerical model, you can share these fractures and create synthetic seismic data. Okay. However, this is like one of the reasons of why we have this distribution of seismic events, why we can create this trend, and that is because the geology of the rock mass, the fractures follow a distribution, and when the fractures follow this power law distributions, and when these fractures are sheared by stresses, the seismic data follows that same distribution or a similar distribution. Now, this distribution of seismic data has been analyzed for large earthquakes, as we can see here, for magnitude from 6 to 8. For large earthquakes, it has been analyzed for mine scale problems with magnitudes around -1.5 up to 0, up to 3 in some other mines. And it has also been found that this relationship is valid for small rock samples that are tested. And when you measure the acoustic emissions, you can see that they also follow this frequency magnitude, and you can adjust Gutenberg-Richter fit onto that. And also you get B values. You can get the B values from large earthquakes data, from data at a mine scale, and also from data at a very small scale. So it's very size independent. And B value also is very representative of the source mechanism. That means on how the rock is fracturing. And that also is usually large values of the B value represent rock fracturing, while lower values of the B value it means there is more shearing associated to fault system or something similar. Now, in this case, we can see some data of seismic data with magnitude and the number of events above that magnitude. And we can just put a model into that. And someone can say, but that data doesn't fit the model. But actually, in this case, this data is not real data, it's synthetic data, and it was created based on that model. So why it doesn't fit? It doesn't fit because there is variability. When you have data, even when it's like very aligned, if you put a fit line into that, you still have some scattered or some deviations from the real data from your model, because your model is just that, it's a model, and you will have some deviation from that. And that is exactly what happens there. You will have some deviations from your model, and that is what you're looking at there. In this case, you have this was like the maximum magnitude that was observed in this synthetic data, and what you will have expected will be something like that. Now, all of those lines that you see there are different realizations of the same statistical parameters. And you can see that the black bars that are being created on the bottom are how many times a maximum magnitude occurs. So we can see that you may have some maximum magnitude around here, but it's very unlikely. Very few magnitudes of that, very few events, maximum events of that magnitude have occurred. Most of the largest magnitudes occur around here. And that happens because this intersection between this line, between the Gutenberg-Richter and the magnitude axis, that generates the mode of the distribution of the maximum magnitude. It's a value that repeats most of the time. But you can still have an event of magnitude 1 in this data set, an event of magnitude 2, and even larger. So in this case, this was done using a simple code that generates this synthetic distributions, and based on all of those realizations, I can calculate the distribution of the maximum magnitude. However, this analysis of maximum this analysis of the distribution of the maximum magnitude has been addressed by other fields of engineering, and it's called the extreme value theory. That that looks for the distribution of the extreme values of a distribution. In this case, this theory looks for the distribution of the maximum magnitudes of your data. So all of that has been described by several in some papers in the mine seismicity field, some by Gibowicz and Kisko on 94, by Lasocki on 2005. They describe the equation that they have the equation that describe this distribution of the maximum magnitude. Westerlu on last year, he also made a very comprehensive description on the methods to calculate this distribution. And so if you can do all of these repetitions, you can just use one of these equations and calculate this distribution of the maximum magnitude. Okay, and that is usually based on the b-value, on the magnitude range, the b-value, and based on that you can generate that. Okay, so from a point of view of the data you have, you can calculate the probability of your largest event. It's not one single value. The largest event is a distribution of values, and you can calculate that probability. Now, what has numerical model have done in this regard? Well, first, it's important to know that numerical methods are, I think that the tool you use depend on what is the mechanism of the rock that is breaking. So Autor and Stacy, some years ago, they described different mechanisms. Hudima and Podvin also, they show in a mine where are located those mechanisms. This is like an example picture from one paper from them. However, Gibowicz and Kisko, he concluded they did a very intensive research on all source mechanism, and they finally concluded the same that is shown in this picture, that there are just two big groups of seismic events: those that are directly related to the volume you are blasting. So you have seismicity close to your volume, close in location, close in time, and you have those other seismic events that occur that are not directly linked to your blast. Maybe they occur further away. They don't occur just after your blast. And usually, the first group is associated with stress distribution around your excavations, and the second group are usually related to faults that are shear. So those are like the two main groups of your source mechanisms. So it depends what is the source mechanisms of your problem, what kind of numerical tool you may want to use. So Hoffman has used some energy release rate analysis to measure stresses and seismicity around longwall mines in South Africa. Me and Vasquez on 2014, we analyzed using a fault slip model, seismicity on, we use a fault slip model, a map-3D model that allows fault slip to calculate seismicity that was interpreted as seismicity associated with faults. Lelkovich and others on 2015, they did an abacus model for nickel ring mine in Canada, and they tried to represent seismicity around the stopes that is caused by the stress distribution, but they also use some but they also do a model that could allow to make calculation for a slip of on faults. Okay. So those are some of the results some results based on ERR, energy release rate. Podlin and others, they make this time series. When you see in the horizontal scale, you see some you see time, in this case is date, and in the vertical axis you see some measure of some seismic parameter that you obtain from numerical modeling. Usually that parameter is like is seismic moment, because seismic moment is something very easy to obtain from a model. It's like the area times the displacement times the stiffness of the medium, and that is easy to calculate from a model. That was another calculation done by Hoffman, where you can see the energy release rate as it progresses in time. And that was another calculation from a numerical model, where you can see the results also on seismic moment for two different mine sequences and how that seismic moment varies over time. In this case, each of these calculations, that calculation there, each of those points correspond to all the deformation, all is a representation of all the seismicity that happened during all of that step. Okay, it's just one value that represents all the excavation step. However, all of those models just generate one value. To consider more than one value, but consider the distribution of seismic data, there are some other models that have been built, like this one that was done by Board on '94 as part of his PhD thesis. He did something like introduce fractures into a 3-deck model, U-deck and 3-deck models. So he was simulating the fractures of the rock, and then he just put an excavation. The excavation induces stresses, and those stresses make those predefined fractures to shear. And each fracture, then when it was sheared, it generated a seismic event, as those there. And based on those events, he could build a frequency magnitude distribution. Mendeki and others on 2001, he did something similar, but using Map3D. Map3D is an elastic model, but allows you to put plastic fault planes. And in this case, he just put a plastic fault plane, and he used different strength properties on the fault. Okay, and based on that, he could also build some frequency magnitude distributions. So then you have the observed data and your model results. Beck also proposed a method where you can calculate the probability of having some magnitude. Where he can link the probability of having seismic events of certain magnitude in certain zones of your numerical model. For example, he just count how many events of magnitude 2 you have in here, how many events of magnitude 1 you have in here, and then he did this. He put like that in a probabilistic way, so you could know the probability of having an event of magnitude 2 in this zone, the probability of having an event of magnitude 1 on that zone. And based on that, he also created a frequency magnitude distribution. Also, that was this work from Kao on 2018, where he also he introduced fractures into I'm not sure if it was a 3-deck model or a flag model, but he introduces the fractures, and then he makes the fractures to fail because of an excavation that was in there, and he calculated the displacement on those fractures, and based on that, he calculated a magnitude similar to what was done by Bohr. and he can also get a synthetic distribution of seismic event, and he compared that with the real data and get very similar values. So all of these methods create a simulation of the events that are actually happening there. However, as we discussed previously, this distribution is just one of the many distributions that can happen. We can just make a fit there. And we know because of what I showed you before that there is a distribution of maximum magnitude. This same model could be something like that, or could be something like this, or there are many other realizations for that same model. To address that issue, when I did my PhD thesis, I did something similar to what was done by Mendeki. I just generated a fault plane with different asperities that when the asperity is sheared, they generate a frequency magnitude distribution. However, I did not create just one. I create several hundreds of fault planes, all fault planes with the same statistical model, but different realizations of the same model. So based on that, I don't have just one frequency magnitude relationship, but I get like 300, 400 of them. And based on that, I can calculate a distribution of those values. So this last approach is very useful from the point of view I'm discussing here, because it allows you to calculate all the distribution of the maximum magnitude. Also, it was very useful because as there were different realizations of the asperities distribution. In some case, the mine sequence just crossed through an asperity, but in another realization, the mines or the channel just crossed at the side of the asperity and did not create a seismic event. And that means that in a time history, the seismic moment that was created, seismic moment is a parameter, a seismic parameter, the model seismic moment was not the same for all realizations. That means that, for example, in this realization, most of the deformation, the seismic deformation occurred on step 10. However, in another realization, most of the deformation occurred on step 9. Okay, so there's also a variability on the time scale. However, this model requires you to create, if you want to do this kind of simulation, you have to make a new model and you have to create a lot of repetitions, a lot of realization of the same statistical model. So it takes a long time to run, and maybe it's not a long time to run now. Computers speed up very, very fast, but you have to build something new, a new model to make this happen. So some conclusions from this literature review part is that seismic hazard is not just one number, it's a distribution of values. Numerical methods, some of those methods provide just one value, like the seismic moment of a specific step, and just that. And the other methods, what provide is like one of the distributions, one of the possible distributions of seismic data, but we know that there are many other distributions. Okay, so now I'm going to speak about a way to generate a synthetic distribution of seismic data that implicitly creates all of this distribution of maximum magnitudes. So, as I mentioned, many of the results from numerical models show that in time you have a variability on, you have you have different values of seismic moment as it changes over time. And so these were the results from Johnny Schober, from Podbin, and they have results like that. So you have a mining step and you have seismic moment, or another parameter that can be related to seismic deformation. And each of these values correspond to all the seismic deformation that occur during that step. Now, seismic moment values are numbers, really large numbers, like to the power of 12, 13. So for this work, I will convert that moment, seismic moment values to a moment magnitude. So I will use a very used formula that converts seismic moment to moment magnitude, and we get the same data. It gets something like this. Okay, it's the same, but it was converted to a moment magnitude. So this magnitude represents all the seismic event that occurred during this period, during this excavation step. Now we know that we don't get one very large seismic event at the year. What we got is several seismic events, a lot of very small seismic events, and a very few very large events. But it's not just one, it's a distribution of seismic events. But what this example do, like the data that has been calculated by Schoberg, by Potvin and others, just calculate one value per step. The step can have several months, several days, and we get this value, which is the equivalent magnitude for that step. And we know that seismic events is not just one, it's a distribution of events. And what we're going to do is to create a set of seismic events that are similar to this one. So all of this data, this is an histogram of seismic events, but all of these seismic events are equal to this equivalent magnitude. So now that I have this set of equivalent seismic data, I can create a frequency magnitude distribution based on that. And I get something like this. So, and I can calculate the B value from that distribution. Now, the important thing here is now that I have this Gutenberg-Richter relationship, I can use that, and I can use the equations I showed you before to generate this distribution of maximum magnitudes. So there we have the equivalent magnitude that comes from numerical modeling, from these models that, like the ones that did Potvin, the ones that I did myself and Vasquez reference in some previous slides, like the ones that did Johnny Schoberg. And based on this magnitude, we get this synthetic data that all the deformation of all of this data is the same as the deformation of this single equivalent magnitude. And based on all of that, we can create this synthetic distribution. And based on that, again, we can use equations that already exist to calculate the distribution of the maximum magnitude. However, sometimes it's more useful to calculate the probability of exceeding a specific magnitude, like this chart that calculates the probability of exceeding, for example, this magnitude. Okay. So this way you can use numerical models, you can use the results of existing numerical models to calculate the probability of exceeding a specific seismic event. So that is like theory, and I will show you a couple of case studies. One is an hypothetical case, just to get an understanding on how can this be used, and the other is a real case study of a block cave mine and this was based on a paper published by Potvin and others, the same I showed you before. I just took that data, and based on that, I calculate the probabilities. So in the case of the tunnel, I just simulated a tunnel that was parallel to one fault and was crossed by other several smaller faults. This is just a simulation on how that was simulated. This was done using Map3D, and the displacements on the faults are plastic because Map3D allows plastic displacements on the faults. So based on that, we can just calculate the equivalent magnitude for each excavation step. However, as we discussed previously, the equivalent magnitude can be decomposed into this synthetic data, and we can calculate the distribution, the Gutenberg-Richter fit here. We can get this value that is called the A over B value. And we can also calculate using the equations shown at the beginning, this line that corresponds to the probability of exceeding a specific magnitude. Now, in this case, this picture is just like a snapshot of one period. We would like to have it for each period to see how the probabilities change over time. So what we're going to do is to use this as a color scale and plot it at each period, at each excavation step. And we can get something like this. So how can you read this rainbow? This represents the probability of exceeding a specific magnitude. For example, in November 2019, the magnitude of 1.5, the probability is given by the color scale. So this color should be something around here. It's a 50% of probability of having an event larger than that. However, if you see in March of 2020, there's a higher probability of experiencing that seismic event because on how the model calculated the displacement on that stage, but it's more likely to have it. So this is what this method allows you to do, to calculate. This all is based on a numerical model and allows you to calculate the distribution of the maximum magnitudes. And because of that, you can calculate the probability of having an event larger than a specific value. This can be very useful, as I show you in the first slide, to calculate the energy, the probability of exceeding a specific energy demand. I will just show you another case study of a block caving mine. This is like a referential picture, but it was based on the data that was shown, that was used by Podbin and others on 2010. So I recreated the data, which is these lines. This corresponds to the seismic moment of 3 different fault systems. So this is the cumulative seismic moment, but in this case, I will use just the absolute, and I will just make the subtraction and get the seismic moment, and then I get the equivalent magnitude for each period, for each excavation step. And based on that, again, I did all the calculations I showed before, and I get this color scale. And I have superimposed there the real seismic data for that same time window. And we can see that in these zones where we have a higher probability of larger events, we actually have some larger events. And the other periods, the other time windows with lower magnitude, we actually have lower magnitude events. So again, I think this is very useful because allows you to quantify based on modeling the probability of having an event higher than a certain magnitude. This tool is not like a magic tool. It depends on how well is your model calibrated. If your model is not good, this tool, this add-in to your model will not work either. You need to have all of this is based on the quality of your model, on your calibration, on how your model represents reality. Okay. So like the conclusion of this work is like, well, the first conclusion we discussed previously is that seismic hazard is not one value, but a distribution of values. and you can calculate the probability of exceeding a specific value. Numerical methods, many methods to calculate seismic hazard or seismic potential, they just calculate one value that corresponds to the, in this case, I check here, it was like the seismic moment, but it's just one value. And stochastic methods, they just show one of the possible distributions of seismic data. So the new conclusions from this is that you can use existing models to create a synthetic distribution, and that synthetic distribution can be utilized to create this distribution of maximum magnitude, and that can be used to calculate, for example, the probability of exceeding an energy demand, which is useful for support calculations and also all the economic aspects of a risk analysis. Before ending, I would like to thank to the mining department of the University of Santiago, el Departamento de Minas de USACH, for supporting this research. To the MXRAP consortium, they provide this great software that created all of the charts I show you here. Map3D, that also provide the software to do this research, and also Itasca Chile, who they also provide the software for our investigation. And just one final thing, if you like this topic, I invite you to submit to do, if you like this topic and you do research on this, I invite all of you to the RASIM next year. So you can just put your abstract. So the abstract is up to the end of this month. So you still have some time, and it's a very great congress that occurs to discuss seismicity and rock bursts. Okay, that was all. Thank you very much.
Thanks, Juan Andrés, for your interesting presentation. Good to know about the RASIM conference. Know now the deadlines. So I want to open the floor for questions. You can do it just, you can write them, in the chat, or you can raise your hand in case you have a question for Juan Andrés.
Hello to all. Excuse me for my English, but it's not. I know that it's not the best, but I have a little question related to the definition of the maximum magnitude of the events. Now, based on the procedure that Juan described, we can calculate the distribution of the largest event. But in the mining industry, we frequently need to define a single value related to the largest event that we can reach. So based on that, I need to know, I want to know, what are your suggestions related to the definition of this largest event?
Hi. Well, as I mentioned, and it's very has been described in many books and papers, is that when you get this maximum value, the maximum magnitude, let me erase this. I will make a picture here. So when you get your seismic data, something like that, you usually do something like that. In some cases, you use like a truncated Gutenberg raster. That is like another option, but you use something like that and you calculate this value. That is the A times B value. The meaning of that is not the maximum magnitude that you can experience. I show you that there is a probability of having events larger than that, However, the A times B value is the most, is the mode of the distribution, is the value that repeats most. But that doesn't mean that you will not have larger events. What I think is the best thing you can do is calculate this from, do the calculations and do a probabilistic analysis and calculate what is the probability of having an event above a specific magnitude. And that is based on your rock support design. When you design rock support, was designed to contain a rock burst based on a seismic event of a specific magnitude. For example, I have designed a rock support that should contain a 1.5 seismic event. So I could go and check what is the probability of having an event larger than 1.5. That is like an important value for me to know. What is the probability of that support system to fail? Or you can keep calculating this value, the A over B, but you need to be aware of what you're calculating and what is the meaning of that. So you don't give a false impression to other people when you communicate that value. I don't know if this solves your questions.
Sure. I want to know that because the definition of this magnitude take some risk, define the risk that we take when we select this value, because as we say, with this value frequently we define the rock support or take another decisions.
Well, yes, as I mentioned, it depends on how you want to face your risk. When you just take the A times B value, when you just take this value and use it, you don't know the probability that, or you use another value, you don't know the probability that your seismic events will be larger than that. So I would suggest you that do the probabilistic analysis of that, so you can know the probabilities of something to fail. Or on the other side, if you just want to design something, you can start what probability will your support be able to withstand? You want to build a support for the 100% of all cases, that will be a very strong support. Or you will say, I will allow a 1% of failure. So that moves you to the right, but not to the end. So you know so you can know your probability of failure. And when you know your probability of failure, you can have your probability and you can know the cost of that failure. So then you can do a risk analysis, and based on that, you can calculate your optimal support.
Okay.
Hello.
Claro?
Hello.
Yeah.
Yes. Can I please? I have one question.
Yes, go ahead.
If we have, for example, seismic data from accelerometers or accelerographs, how can we know what is the threshold from which we can say that we will have, or predict that we will have a rock fall or rock burst? How to fix the threshold?
Can you please explain me a bit what you mean about the threshold?
It's for example, we have the diagram from the accelerograph, and then we have, for example, one peak in the diagram.
Okay.
And so what is the limit from which we can say that if we have this peak, so we will have a rock burst or a rock fall?
Okay, well, usually all of these analyses are based on seismic data, and seismic data is the result of processing your geophone or accelerometer data. Your seismic wave has to be integrated using like a Fourier transform or some methods that usually the computer do that, and you can get from that one magnitude. When you have several events, several, I mean, under 100 events, you can create a relationship like the one I show you here, in this, in here. In this case, I have many thousands of events, hundreds of thousands of events, but still, I think with like 100 events, if the events correspond to one group of seismic data with the same source mechanisms, they should align, and you could do some of this analysis. But you first need to use that seismogram and calculate the seismic parameters, like the magnitude, like the, well, in this case, just magnitude, it's okay, but you need to analyze and process those seismograms.
Okay, thank you.
No worries.
Thanks, Pedro. I have a question from Eduardo Bonilla. It's about the importance of data quality management for models. I don't know if Eduardo is still here. If you want to ask the question by yourself, or you want to specify something.
Puedes preguntar en español también si alguien quiere. I'm not a native English spoken person, so.
Oh, no worries, it's okay. We are on the same page. No worry. Probably here have Italian people.
Buenas tardes, profesor.
Eduardo.
Hola, hola.
Hola, buenas tardes. No, básicamente poder darle la importancia a la calidad y al manejo de los datos para poder modelar, en el fondo, eso, como resaltar eso o la importancia de cuando uno tenga que administrar los datos y poder establecer en la mina, poder manejar esos datos. Hacia allá, más que nada, ya me consulto. ¿Cuáles serían las recomendaciones que usted propone?
Bueno, lo importante, well, the question was about the data, having the, how to manage the data you have on the mine. And I'm thinking, pienso que la información que tú tienes que tener, lo ideal es que tenga información, si quieres hacer un buen modelo, tienes que tener información de tu secuencia de extracción, que tenga información de tus tronaduras que están haciendo, tu extracción, y en base a eso hacer un modelo y después tú poder correlacionar ese modelo con tu sismicidad. Si tú no tienes información de tus tronaduras, tú no sabes cuándo la haces, de repente no sabes la extracción que estás haciendo, hay minas de repente que no guardan todos esos registros, después no va a poder hacer una buena simulación, porque no va a ser algo que sea representativo de los cambios que están ocurriendo en el macizo rocoso. Entonces, en ese sentido, es importante tener un buen manejo de qué es lo que está pasando en la geometría de la mina. También, por supuesto, es importante saber todos los temas geológicos que están ocurriendo, la litología, principalmente las fallas que hay, dónde ocurren. Y eso pienso yo que con respecto a la información. So,
okay, profesor, gracias.
El problema. He was asking about what about data management to create these models, and I was mentioning that you need to have good quality data about your mine sequence, the mine sequence you mine, or if you have a tunnel, how you are advancing your tunnel, so you can create models that are representative of the real world real excavations you are making, and that way you can find better correlations between your model and your seismicity. Yes.
I was mute. Thanks, Juan. Thanks, Eduardo. I think we have time for another question.
Yes, hello. Thanks for the presentation. I have a couple of questions. So basically, the first one would be if there is any kind of filtering for the data you show. So I was wondering if we might be able to get the same patterns as you just show if we take data from the entire mine site. So my question would be, for this kind of seismic processing, are we considering the data from the entire mine site or just for a given domain?
Okay, thank you. I think it depends on, as I mentioned in some slide, it depends on the source mechanism. Sometimes if your mine has different source mechanisms, that means like in some part of the mine is very caused by stress, high stresses, and in other part of the mine, seismicity is caused by fault slipping, and in other parts is a mixed behavior. I think in those cases it will be better to separate things and use one code to represent one thing and do another code to represent the other mechanism. Maybe there could be some code that could do both things at once, but I will go for sure and do those things separately. Also, for this analysis, yes, this analysis has one specific thing, that when you create your distribution, your synthetic distribution, let me get the slide. When you generate that distribution, this method only works with one source mechanism. When you have faults and stresses working together, you don't get that straight line, so you get a different shape, and I haven't worked on how to do that yet. So again, going back to your question, you have to test your model and see how far can you go on your simulation. Maybe doing the complete mine, if you have a large mine, could be very complex to get a good correlation between your modeling results and your seismicity. Or maybe you can get good results. Anyway, if you don't get good results with your complete mine, maybe you have to go zone by zone, go for a specific zone, then go for another zone, and then compare the results on that different domains. I don't know if that partly solves your question.
Okay, thank you. And just the last question I have is, you mentioned that you use, among the different software you use, you mentioned MXWrap. I was wondering if you could give us some hints on what does the software do and what features does it have. As far as I know, it's not fully commercially available. So if you can tell us a little bit about it.
Yeah, well, MXWrap is a software that is developed by the Australian Centre for Geomechanics. It's mainly used for research purposes, but you can contact them, or I can put you in contact with them, and they can arrange some license for you. The software comes with some modules that are basic, but that are some modules that are done for analysis of seismic data or analysis of geotechnical data in general, not just seismic data. So there are some models that are already like for you to use, but the software also gives you the capabilities for you to program your own codes and use different tools and create a new application like these ones that I show you here. So I think it's a very good software for seismic data, for geotechnical analysis, and if you want to create if you have some idea of some things that could be correlating and you want to write your code and do something new, it's very good for that. So it's a web page. It's called mxwrap.com, I think, and then there you can see more. You can have more information on what does the software do. I will write on the chat the web page.
So thanks, Christian. Thanks all for being here, for attending our seminar that's been organized, as I told you, by the Rock Mechanics Society from France, Italy, and Spain, together with the Chilean group of the Tunneling Association and Underground Spaces. Thanks again, Juan and Andrés, for accept our invitation to present your research work. And please keep in contact with us. There are several presentations that will go in the next months. And so, of course, you are all invited to attend them. And that's it. Thanks all, and have a nice afternoon or lunch, or I don't know, wherever you are. It will depend. Bye-bye to all.
Bye-bye. Thank you very much.
Thank you.
Thank you very much.
Thanks.
Bye-bye.